Welcome back to The Explainer. Listen, if you're a focused learner aiming for absolute surgical precision in your exams, you are in exactly the right place. I'm stepping in today as your master coach, and we are diving into a true high-stakes masterclass covering the Cambridge Mathematics 9709 syllabus. Specifically, we're taking on a giant of the AS and A-level curriculum. We're talking mechanics. We're focusing entirely on friction, that famous equation F equals mu r, and the absolutely critical concept of limiting equilibrium. Now, over my years of analyzing global examiner reports, I've seen exactly where candidates forfeit marks. To help illustrate this today, I want you to picture two types of students in our digital testing suite. We've got Scholar 1, let's call him Alex. Alex overloads his paper with raw factual definitions but completely fails to provide deep analysis. And then we have Scholar 2, Sam. Sam is a fast writer, constructs highly persuasive arguments, but entirely misses the explicit restrictions set by the Cambridge command words. Today, we're going to deconstruct both of their approaches, analyze the marking structures in real time, and give you the ultimate tools to secure those top-tier mark bands.
So why are we dedicating an entire exhaustive explainer to this single topic? Because the stakes are literally game-changing. This specific area of mechanics accounts for approximately 15% of the total marks in Paper 2. Think about that for a second. That is a massive chunk of your overall grade resting on your ability to not just understand friction in a vacuum, but to prove to the Cambridge examiners that you understand it according to their very rigid, very specific marking rubrics. As we go through this session, imagine a mark yield meter tracking your performance. We aren't just trying to bump you from a C to a B. Mastering this specific tactical approach can entirely shift your performance tiers straight up to a clean A or A star.
And the absolute crucial point comes straight from the global principal examiner reports. They state, and I quote, "The classic mistake is providing generic answers not specific to the question context. This is where our friend Alex always loses marks. The examiners are practically begging candidates to stop memorizing textbook definitions and pasting them into the exam regardless of what the problem actually dictates. If you have a block on an inclined plane with a rough surface, your math, your resolving of forces, and your written reasoning must directly reflect that specific physical scenario. Generic simply does not get the grade. If you write out a generic definition of friction without applying it to the specific angle of the plane or the specific mass of the particle, you trigger an immediate marking penalty on the examiner's grid."
Okay, so here is our exact structural blueprint for today's session. First, the core principles of equilibrium. Second, the method mark strategy. Third, the top 3 examiner traps. And fourth, the compliance audit protocol.
Let's dive straight into Section 1, the core principles of equilibrium. Let's establish our foundational baseline and decode a high-tariff target question. Picture a complex, multi-part Cambridge past paper question on the smartboard. The core concept at play is limiting equilibrium. This is defined as the exact threshold state where friction reaches its maximum possible value before motion occurs. This is the precise, and I mean precise, moment where the equation F equals mu r actually applies. F is the frictional force, mu is the coefficient of friction, and r is the normal reaction force. Now here is where we need to talk about command words. If the question says state the condition for limiting equilibrium, that's a basic recall task. But if the command word is evaluate the forces acting on the particle when it is in limiting equilibrium, you can't just define it. Evaluate means you must calculate the forces, weigh their impact against each other, and draw a conclusion based on the math. Our student Sam loves to ignore these command words. If it asks to explain, Sam will calculate, completely missing the qualitative requirement. Remember, the key word in this definition is threshold. It's that microsecond where an object is pushed to the absolute brink but hasn't yet started sliding. If it's just sitting there comfortably with no impending motion, F does not equal mu r. In that case, friction is merely balancing the applied force. It could be far less than the maximum. You only deploy this equation when the object is on the absolute verge of moving.
Understanding that mathematical distinction is exactly what the assessment framework tests. Let's break down the precise assessment objectives, or AOs, demanded by CAIE marking rubrics. The examiners are targeting 3 distinct cognitive domains, scaling up from foundational definitions to high-level analysis. For knowledge and understanding, or AO1, you need precise definitions and to show causal relationships. This is Alex's comfort zone. He knows exactly when to state F equals mu r. But you can't stop there. For application, or AO2, they want to see you integrate this with other syllabus areas. And for analysis, or AO3, the required action is logical, structured reasoning. The examiners prioritize deep analytical thought over superficial breadth. They want to see how you step-by-step think through the mechanics. If you misinterpret the command word, say confusing describe with analyze, you stay stuck in the AO1 domain and forfeit the massive points locked away in AO3. Here is the real secret to unlocking those highest tiers of the mark scheme. Top-scoring candidates absolutely do not view friction in isolation. Let's transition to Alex and Sam in their shared study suite. They're trying to draft a model response for a brutal 6-mark mechanics question. Alex looks at the problem and immediately starts writing a massive block of text. He writes, friction is a resistive force. The coefficient of friction is constant. Therefore, F equals mu r. He focuses entirely on textbook data inputs. But Sam slams his pen down and says, no, look at part B. The block accelerates after the force is increased. Sam is fighting to build a flexible, analytical thesis link. He knows that if a friction question leads into an acceleration problem, you must bring in Newton's second law. The force applied minus the maximum friction equals mass times acceleration. The students who seamlessly connect those two concepts, friction and kinematics, are the ones who watch their mark yield meter max out. You literally have to view the entire mechanics syllabus as an interconnected web, challenging your own reasoning at every step.
Which brings us perfectly to our next critical section, the method mark strategy. Okay, strategy check. We are about to look at the exact procedural framework to build a repeatable pipeline for success. But before we unlock this top-band paragraph structure to help you crush your upcoming sessions, make sure your revision feed is perfectly optimized. Take a second right now to subscribe to Ace the Exams at Ace the Exams and enable all notifications so you never miss our weekly Cambridge exam breakdowns, no matter if you are sitting for IGCSE, O-levels, or AS and A-levels. All right, let's get back to the study suite. Alex and Sam have hit a massive structural roadblock mid-paragraph. Their mathematical evidence is solid, but it's totally failing to link back to the main thesis of the question. Here is where we deploy a universal structural matrix to fix it. Step 1. Extract data from texts and tables. You must pull the exact values given in the scenario. Step 2. Apply proper formatting and terminology. Draw your free body diagrams right away. Step 3. Draw evidence-based conclusions. We are going to use the Peel framework here. Point, evidence, explain, link. Your point is identifying limiting equilibrium. Your evidence is resolving forces horizontally and vertically. Your explanation is showing the algebraic substitution of F equals mu r. And your link is stating whether the object accelerates or remains stationary based on that math.
Let's actually rewrite Alex and Sam's text out loud line by line to engineer a flawless top-tier response block. They need to adhere to strict procedural conventions. So first line, we write, resolving forces perpendicular to the plane. That's our clear annotation. Next line, r minus w cos theta equals 0. Therefore, r equals w cos theta. That's correct terminology and appropriate formatting. Next line, because the particle is on the point of slipping, limiting equilibrium is reached, hence F max equals mu r. See that? We didn't just throw the equation on the page, we gave the procedural justification for it. Finally, resolving forces parallel to the plane, P minus F max minus W sine theta equals 0. You could be a mathematical genius, but if your work is a chaotic mess scribbled in the margins, the examiner cannot and will not award you those vital method marks. Clear annotation acts as a signpost. It proves practical application, and it is exactly what Cambridge is looking for.
Let's pivot now to the Insider Intelligence segment, the top 3 examiner traps. Welcome to our interactive pause and practice visual workshop. I am addressing you directly right now. Challenge 1, the visual data scan. Imagine a complex diagram on your paper, a mass of 5 kilograms on a rough plane inclined at 30 degrees, connected by a taut string over a smooth pulley to a hanging mass. A 60-second countdown timer is running in your head. You must extract the highest yielding core trend before the clock runs out. What is the trap here? The trap is confusing cause versus effect. In mechanics, you must draw a stark contrast between the physical trigger and the mechanical result. Gravity pulling the object down the slope is the cause. The frictional force acting up the slope to resist it is the effect. If you panic under the 60-second timer and set up your equations backward, if you confuse the driving force with the resistor force, the entire structural integrity of your answer collapses. Friction always opposes the direction of intended motion. Identifying that direction in the first 10 seconds is your highest yielding move.
Challenge 2. Spot the examiner trap. Let's look at a flawed, medium-tier student paragraph pulled from the archives. The student writes, the object is stationary. Friction opposes the pulling force. I used F equals mu r to find the friction as 12 newtons, which is less than the pulling force of 15 newtons, so it moves. Okay, where is the exact line where the logic drops the mark? Let's use our digital highlighter. The trap is right there. I used F equals mu r to find the friction. You cannot use F equals mu r unless you explicitly prove or state that the object is in limiting equilibrium. If it's stationary, friction might just be balancing the pull. The student provided a generic answer, not linked to the scenario's constraints. They forgot to check if the format of the question actually allowed for maximum friction. They fell right into the top examiner warnings, confusing cause and effect, sloppy presentation of logic, and generic reasoning.
To ensure you never make that mistake, we move to the final evaluative stage, the compliance audit protocol. This is how you elevate an answer from being just good to being genuinely top tier. Let's review Alex and Sam's final high-scoring response. They have realized that to hit the critical analysis requirements, they have to audit their own work. The protocol demands that you identify both similarities and differences in physical states. You must use comparative connectives. For instance, writing, whereas the smooth pulley system creates constant tension, conversely, the rough plane introduces a variable frictional force up to a limit. You must support every single one of these comparisons with mathematical evidence derived directly from your calculations. And finally, justify your decisions. Don't just leave a number like mu equals 0.4 dangling at the bottom of the page. Tell the examiner what that number means for the physical system. Since mu is 0.4, the maximum frictional force exceeds the component of weight down the plane, therefore the system remains in equilibrium. That right there is peak evaluative thinking.
To help you retain these complex, interwoven relationships under the extreme pressure of the exam room, our curriculum sources highly recommend a powerful memory hack. You need to encode F equals mu r concepts using a visual story method. Do not just memorize the abstract letters. Imagine a massive, rough stone block. Imagine yourself physically trying to push it. The R is the solid ground pushing fiercely back up against the immense weight. The mu is the gritty, sandpaper-like texture of the surface scraping your hands. The F is the invisible wall stopping your push, growing stronger until you finally break its limit. Build this vivid physical movie in your head. When the exam timer is counting down and the panic sets in, you don't search for a formula, you recall the movie, and the strict mathematical logic naturally follows.
All right, let's distill this entire masterclass into 3 universal Cambridge operational rules. Rule 1, the 3-step question scan. Decode the command words immediately so you know your AO target. Rule 2, the marks per minute formula. Allocate your time strictly based on the tariff of the question. Don't spend 10 minutes on a 2-mark definition. Rule 3, the post-writing compliance audit. Run the Peel checklist on your final paragraph. I want to leave you with this provocative question. Are your answers specific to the given mechanical context, or are you falling into the generic trap? Audit your own recent practice attempts and be ruthless about it. Now it is time to take action. Subscribe to Ace the Exams at Ace the Exams, click that notification bell for our weekly great masterclasses, and drop a comment below right now sharing exactly which Cambridge subject and level, whether it's IGCSE, O, AS, or A level, you are preparing to conquer next. Thank you for stepping into the testing suite with me today. Stay focused and happy studying.